When we're talking about limits, one of the very important properties that happens is when the function that we're taking consideration of is a continuous function. So what you might have learned about continuous functions in your study in pre-calculus and before, sort of the informal way that's discussed is this idea that if you drew the graph of a continuous function, that your pen or pencil wouldn't come off the paper or your marker wouldn't come off the board. Again, that's a very informal way of discussing that. There's a lot more formal way. And realistically, it's actually this definition, so we're kind of working our way backwards. But the idea is that if I have some continuous function, and at some point C, I have the function value. Well, if the function is continuous, what that tells me is that the limit as f approaches C is just the value at C. It is just the value of f at C. Okay, so that's a lot of words, but mathematically what that really means is that for a lot of the functions that we're used to dealing with in math, whether they're just think like polynomial functions or even trigonometric functions, except tangent's a little squirrely there, but in those cases, instead of having to do any sort of fancy techniques when evaluating limits, all we really have to do is plug in the value. So what this tells me is, instead of doing this whole limit behavior as x approaches C of f of x, I can just plug in the value here. What does that mean? That means that for this, the limit of this function x, right, the straight line, the limit as x approaches 3, well, I can just plug in 3 for x, and it stays 3. Similarly, if I take the limit of a constant function, right, so if I were graphing f of x equals 2, that's just a flat line at 2. So it doesn't really matter what x approaches, that value is always 2. So you're not even really plugging in here, but that's an important piece. And also, in this case, x squared, that's the parabola. So the limit as x goes to negative 1, well, we just plug in negative 1 wherever we see an x. So negative 1 squared is positive 1. So these are three cases where we're really not doing anything very complicated. We're simply plugging in the value for x, or in this case not at all, and seeing what's there. And so that's a very nice behavior. But now that we know that about limits, let's move a little further and talk about some generic properties. So if I have two limits, so if I have two functions here, and as x goes to C, this goes to some number, and this goes to another number. So we're assuming that these exist and are finite and whatnot. And if we have some sort of scale value b, the limit as x approaches C of b times f of x is b times L. Well, what does that mean? That basically means that if I have a scalar multiple, if this was 2x instead of x, then the answer would be 6. It'd be 2 times 3. So realistically what that means is that you can factor constants in and out of limits. Similarly, if I take the functions added together, then their limits are added together. If I subtract the functions f of x minus g of x, the limits are subtracted. Don't confuse this plus or minus with the same thing that you think of when you're thinking about like square roots. It's related, but not really. Similarly, if I have two functions multiplied together, I can multiply their limits individually. If I have two functions divided by one another, well then it's their limits divided by one another, except in the case where the bottom limit is 0, because dividing by 0 is undefined. And then finally, if I have a function raised to a power, then its limit is the limit raised to a power. So we kind of saw that over here, where I took the limit negative 1. So if this was x approaches negative 1, I would plug in here, and then I would square it. So that's how I get positive 1. So you're kind of seeing that here. And we're going to do some examples to really solidify this, but ultimately, knowing this and knowing these is going to get you really far when you're dealing with limits.